So we're looking at C10H12O2, and the number of double bond equivalents is going to be 5. Looking at the 5H, you can see that we have an aromatic ring, and that's going to be C6H5. Over here we've got a CH2, a CH2 and a CH3, so that's 2 CH2s, 1 CH3. And what have we got left over? We've got a C, 2 O's and a double bond equivalent. That suggests a C double bond O and then an O as well. So these are the pieces. Now we've got to put them together. Now there's a fair number of ways that this could possibly be put together, but only one of them will fit the spectrum that we have here. Well, let's look at what we're seeing with the CH2, the CH2 and the CH3. Because we got a CH2 with 3 peaks, that suggests that that CH2 is next to another CH2. This CH2 has 6 peaks. That suggests it's next to 5 hydrogens. It would make sense that this CH2 is going to be between a CH2 and a CH3. This is confirmed by the fact that the CH3 here has 3 peaks, suggesting that it's next to a CH2. So what does that tell us? It tells us that the CH2, the CH2 and the CH3 are put together. The other thing that's going to be important here is what we do with the C double bond O and the O. Is it going to be like this, or is it going to be like this? Well, we can actually tell, and the way we can tell is, I have this in the guide, and that is when a peak is next to an oxygen directly attached to it. For example, like in this case, this CH2 is connected to this oxygen. That peak will appear around 4 ppm. This CH3 that's attached to the C double bond O directly will appear at around about 2 to 3 ppm. Is where you'll see it. In this instance, you'll see that the CH3 is connected to the oxygen, so it's at 4 ppm, and this CH2 is going to be at around 2 ppm or 2 to 3 ppm. So that's how you can tell what's connected to what. How does that help us? Well, if we look at the CH2 here, it's between 2 and 3 ppm, which would indicate that it must be directly connected to the C double bond O and not the O. Had it been connected this way, this CH2 would have appeared at around 4 ppm, according to what I just told you. There's one other clue that tells us that the C double bond O is here and the O is here, and that is when we look at the way it's connected to the aromatic ring. You can see that if a C double bond O was connected to the aromatic ring, it would split into 2 portions and would be centered at around somewhere after 7.5 ppm. If there's an oxygen directly connected to the aromatic ring, like we have here, then it splits into 2 peaks, but the peak is centered at around 7 ppm. So always a little bit upfield from where it would be if it was a C double bond O. So using that, you can see that if we have an O directly attached to the aromatic ring like we do here, that's the result we expected. 2 sets of peaks split at around 7 ppm.